Let's get started. Good afternoon, everyone. My name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute for the Theory of Computing. And thanks to everyone, both in the room and in remote, for joining us for today's Richard M. Karp Distinguished Lecture. First, a brief background about this lecture series. We established this series at the Simons Institute to celebrate the role of Simons Institute founding director, Dick Karp, in establishing the field of theoretical computer science, formulating its central problems, and contributing really stunning results in the areas of algorithms and computational complexity. And the series has about 4 lectures each semester and features visionary leaders in the field of theoretical computer science. And the lectures are geared towards a broad scientific audience. And we are really grateful to the many contributors to the Richard M. Karp Fund who have made this series possible. And coming to today's talk, I'm really delighted to welcome today's speaker, Constantinos Daskalakis. Kostas is a professor of electrical engineering and computer science at MIT. He got his undergraduate degree at the National Technical University of Athens. And Kostas is no stranger to UC Berkeley. He got his PhD here. And also to Simons Institute, where he's actually an organizer, a co-organizer of both the programs this semester. I'm not sure if that has ever happened before, so he's a familiar figure here. And in terms of his work, he has done major works at the interface of theory of computing and game theory and economics. And he has proved those all long-standing open problems on the complexity of Nash equilibria and multi-item auctions. And his work has also touched upon many topics at the interface of CS theory and probability theory, machine learning, and statistics. And one of his recent focuses is high-dimensional statistics and learning from uncertain and strategic data. So he has won, his works over the years have been recognized with many prestigious honors. And to just mention a few highlights, his thesis won the ACM Doctoral Dissertation Award. And his most recent awards include the Rolf Lemelina Prize from the International Mathematical Union and also the ACM Grace Murray Hopper Award. So today his talk is entitled Equilibrium Computation and Machine Learning. And please join me in welcoming Kostas Daskalakis.
Thanks very much, Venkat, for the very kind and warm introduction. It is my great pleasure to give the Richard Karp lecture. Yeah, I mean, it's Richard Karp is one of the giants in our field. Very inspiring, very kind person with enthusiasm towards research, and he was a true inspiration when I was a student here. So these are slides by Richard Karp on the visit days when I came to Berkeley in 2004, and sort of like to summarize, one of the aspects of how Dick views computation as transformative, not just for computing, the field of computing, but also as a lens to study sciences broadly. And of course, he was supported in this quest by other people at Berkeley then and now that you see here. And another thing that makes Karp special is, also, I mean, his amazing contributions to the field. And his, what he appreciates in those contributions. So this is a course announcement from when I was a student. I tried hard to find it in my email, but found it today. So the class was called Great Algorithms, and here's an intro to the class that sort of like shows, what Karp appreciates in algorithmic contributions. So from time to time, a new algorithm comes along that causes a sensation in theoretical computer science or in an area of application because of its resolution of a long-standing open question, its surprising efficiency, the novelty of the setting or the approach, the elegance of its structure, the subtlety of its analysis, or its range of applications. We present a variety of these algorithms. mostly drawn from the following list. You can quickly skim through the list. But I think that that little snippet summarizes, the fact that, something about the essence of what Dick appreciated, and what he inspired his students and collaborators to do. I also want to thank Dick for adopting me when I was graduating from Berkeley. So Christos was traveling during the commencement, and he barely missed me. So here's Christos with his fancy Cyprus, gown from Cyprus University, coming from the airport. He barely missed me. So Karp stepped in to adopt me and hood me that day. Okay, so thank you very much, Dick, for being an inspiration and for all your contributions to the field. All right, so let me now dive into the technical part of the presentation. I want to talk about some beautiful points of contact between game theory, optimization, and machine learning. And I'm going to talk about two results. This paper with Stratiskalakis and Manolis Zampetakis, and this very recent work that started last semester at MIT, and we just completed with Noah Golovich and Kai-Shing Zhang while being assignments. Some of you might have seen the first part, but this is the new component that I'm adding to that. So machine learning has made a lot of progress in heretofore challenges, machine learning, learning challenges, and many of these progress from an optimization standpoint looks like becomes a minimization problem. So a lot of this progress is enabled by formulating learning challenges as minimization problems that involve high-dimensional variables and functions, loss functions that are non-convex, and they're essentially only accessible via first-order information, value queries and gradient value queries, and which many times are at least Lipschitz, differentiable and smooth, at least almost everywhere. Now, the corresponding problems are difficult problems. They're NP-hard problems. And because of the high dimensionality of these problems, really, one doesn't have many options for how to solve them. A very prominent, method used to solve these problems is gradient descent, which, of course, is not guaranteed to find globally optimal solutions, but at least it finds locally optimal solutions, which in practice work well for a lot of those applications. In the past few years, we've also seen an emergence of multi-agent learning applications, from playing difficult games to multi-agent interactions involving robots or other agents, to applications that are not explicitly game theoretic, but where a game theoretic formulation enables us to attain learning outcomes that are useful, such as training deep generative models and protecting classifiers from adversarial attacks. Now, those formulations are not optimization problems, but they correspond to games and involving multiple agents. And those games, in those games, the agents make high-dimensional decisions using vectors, high-dimensional vectors in some constraint set. They often those agents often impose constraints on each other. Like if a robot goes somewhere, maybe another robot cannot go to the same place. So I'll be denoting the constraint set by S, constraining the joint actions of all agents. And like what was happening in the minimization space I was talking about before, the utilities functions of those agents are typically non-concave in an agent's own actions. Equivalently, the loss function that an agent wants to minimize is not convex in their own actions. And that is a big departure from the settings that classically are studied in game theory, where typical settings in both game theory and economics involve agents who try to maximize a utility function that is concave or quasi-concave in their own actions. So here, very naturally, you get games where agents are maximizing non-concave utility functions. And that's a big departure, as I'm going to describe shortly, from the classical setting. Also, typically, agents don't really know a closed form of their utilities functions. They can interact with their utility function. They can get function value queries or gradient function value queries, but the higher order information becomes more and more expensive. And as before, I mean, many settings, those utility functions are at least Lipschitz differentiable and smooth in an agent's actions. So I'm going to be calling these games smooth because of this property, non-concave games because of this non-concavity of the utilities. And what makes these problems challenging is that a lot of game theory goes out of the picture the moment you introduce non-concavity. For example, equilibria do not exist in these non-concave games. And this is a trivial example where this happens. Two players, zero-sum game. One player wants to come as close as possible to the other player. The other agent wants to go as far as possible from the other player. There's no equilibrium in this game.
What do you have against mixed strategies?
Excuse me?
What do you have against equilibrium mixed strategies?
You could consider, you could try to convexify the setting by playing distribution on this constraint set. And you may or may not have equilibrium existence then. Even if you do that, you may not actually have equilibrium existence. And a game where this happens, for example, is the guess the larger number game. It's a zero-sum game with two players. Whoever reports the highest number wins a point from the other player. You get, basically players chase each other to infinity in this type of game. So this has been studied in the literature, but yeah, it's not mixed strategies is not a magic wand, okay, that you can use. But also from a practical point of view, you don't want to have distributions over parameters of a deep neural network, right? So yeah, so but certainly this is a direction that is worth studying and has been studied. But anyway, so these games do not have equilibria, and the main goal of this line of work is what are then meaningful solution concepts in this setting, and are they practically attainable? So by meaningful, I mean that at the very least they should be they should exist in every non-concave game, and they should be verifiable with the information that agents have about their own utilities. By practically attainable, I would like them to be also efficiently computable via some lightweight method like gradient descent or something like that.
Yeah, I don't know if this distinction matters, but something that just picked up from the last thing you said in response to the last question.
You want to use the mic?
Oh, sure. So it seems here like you're talking about whether you have concavity in the decisions, but in just a moment ago, you said something about concavity in the parameters of the deep neural network, which might be something that induces the decisions much higher dimensional than the decision space itself. Is that distinction going to matter to us? I mean, should we? I mean, otherwise, it seems pretty natural to think about discrete parameters that induce a distribution over decisions.
So let me give a concrete example, and then let me return to your question. Okay. Yeah, I mean, a motivating example for this line of work is training deep generative models. The goal of deep generative models is to is to find parameters of a deep neural network that has the following interesting property. It takes as input boring randomness, so samples from an isotropic Gaussian, and outputs interesting randomness. For example, faces that could be coming from the probability distribution of celebrity faces sitting in some platonic space, right? So, how do people? What is one way to get parameters for a neural net achieving this very nice property? A proposal by Goodfellow et al. Is to set up a two-player zero-sum game between two agents, an agent controlling the variables of this neural network, and another agent controlling the parameters of a different neural network, who is trying to distinguish between real samples and fake samples. Okay, so this guy takes as input boring samples and is supposed to produce good samples. This guy is getting samples that are either coming from the generator or from the true distribution of celebrities. And is supposed to say 1 if they see a true sample and 0 if they see a fake sample. They want to distinguish between the two distributions. There are many ways people assign utilities to the players of this architecture, but here's one called Wasserstein-Gans by Arczowski et al. Over here, you ask the discriminator to maximize this utility function written here. This utility function is the expected difference in the output of the discriminator when you plug into the discriminator a real sample versus a fake sample, a sample that has gone through a neural network and into the discriminator. So you ask the discriminator to maximize this utility function. You ask the discriminator to minimize this utility function. And here you see how the decisions made by the players of this game, are parameters of neural networks that come into the utility function, causing this known concavity in the utilities. Now, to come to your question, Kevin, I guess you could say, like rather than choosing parameters of a neural network, let me choose a distribution over faces. Okay, that is too high dimensional and impractical. There's no good description of how good parametric description of how this may look like. And here you're postulating that maybe parameterizing this distribution as a neural net could lead to good samples. All right, so coming back to the original thread, so you see here how, with this interaction of neural networks, you see how non-concavity may arise. And to my previous point, equilibria do not exist in this case. There's no X and Y that necessarily are an equilibrium of a general problem like this. And in the absence of such a solution concept, the question is, what does game theory predict in this case? Okay, so maybe game theory says, okay, you should convexify the setting somehow, impose some compactness, do this or that or the other, and maybe equilibria start arising. That is a possible avenue, but is not really what would be a practical solution for this setting. Yeah.
I'm just curious in this, excuse me, in this GAN example. So typically it's non-concave. Are there rigorous results saying that, say specifically for Wasserstein-Gans, that equilibria don't exist?
You can construct, yeah, you can construct easily, yeah. Cases. Okay. And you can also construct cases where they do exist. So.
Okay, in both ways. Thanks.
Yeah.
Just to follow up on the previous question, in the space of, as you said, distributions and like classifiers, it's convex concave. So you still have a equilibria in that specific space, no?
Correct, I agree with that. No, I agree with that. So you could talk about distribution over, you could talk about general distributions, but what I was saying earlier, this is not practical. So you have to, what you do here is you parameterize the distribution in a way that actually leads to good results. Or you could have, you could have one player searching the space of all possible functions to classify, and another player respect to all distributions over, a million dimensions. Yes, maybe the problem will be convex there, but now you're hit with a lot of statistical issues, right? Like if you think that the world is sampling a general distribution in a million dimensions, like 1,000 by 1,000 pixels, then, statistics tells you that you need exponentially many samples in a million to be able to, learn a distribution. So that's not a good way to go about this problem because of statistical issues.
It doesn't give tractable methods to complexity.
Correct.
It gives a target. You could consider that with your...
Correct, but I guess Let me put it this way. Let's take that over, the discussion section, because this is not even the main point of the talk. It's just an illustrative example of how you get non-convexity in general, right? So now, okay, coming back to this equilibrium that exists, what do people do about it? Well, people try. And what they try to do is to have agents run their own methods, their own gradient descent method to optimize their own parameters. So they do this simultaneous gradient ascent in their own utilities. And practically, this is very problematic. So oftentimes, having the two agents of such a game run their own variant of gradient descent leads to either cycling behavior or leading to bad solutions, not what you would like to happen. Okay, so these are two examples are showing a target distribution. So in here you want to sample not from faces but from handwritten digits, and here you're seeing what the generator is sampling if you stop the training at different steps. Over here, the target distribution is a mixture of Gaussians whose means are in a cycle. And again, here you see what the generator generates if you stop the training at different steps. People add a lot of bells and whistles trying to stabilize gradient descent in these types of settings, but it is a challenge to train. And that was given as a little example to motivate, how non-concavity arises, and the lack of equilibria, and the types of questions that arise, motivating the question that is here on the slide. Okay, so let me start with a simple idea for what would be a local notion. Okay, so like I was saying earlier, that in a single agent setting, we are targeting local minima as opposed to global minima. What if we try to do something similar here? Okay, so this would be the analog of local minima or local maxima. So I'll say that a strategy profile X star comprising an action for each agent is a first order local Nash equilibrium if the following condition holds for every agent. Let's try to parse it. So here, what's happening is that the agent is trying to do a gradient ascent step, trying to improve their utility, keeping the actions of the other agents fixed, and trying to do a gradient step with respect to their own variables from this point xi star. All right, so they try to make an improvement. Then they project. Remember there were constraints that tie everybody's decisions. So they try to make an improvement. They project back down to the constraints imposed on them by the actions that the other agents choose. And if that attempt doesn't go anywhere, I'm gonna say that the point is a Nash equilibrium, is a local Nash equilibrium. The agent attempts to improve, but they don't go anywhere. Okay, I'm going to be calling that a local Nash equilibrium. So pictorially, a local Nash equilibrium is a point x1 through x1 star through xn star, such that every agent finds themselves in one of these two situations. So this orange shape is the constraints imposed on agent I by the other players. These are the set of actions by everyone else. So this is the constraint imposed on agent I by the actions of the other players. So a player is at a local optimum if one of these cases happens, right? So either what they're playing now is on the boundary of this constraint set, and if they try to make a step to improve, they're going to land at a point that is outside, and projecting down into the set, it gives them the same point. Or they're inside, but the gradient is zero. So first order information doesn't tell you, anything about what to do locally. So a local Nash equilibrium is a point where the action played by agent I is a best response to the action played by the other agents, at least as far as the first order information, the first order approximation to an agent's utility function is concerned. This is what is the natural generalization of local minima in this case. All right, so this is a relaxation of Nash, right? So Nash would tell you that no matter where you go, you can't improve. Here, you're only asking about a greedy step using a first order approximation to your utility. So it's a relaxation. So at the very least, that this would be stable. And the question is, does it exist? And it's actually pretty easy because of this fixed point form that it has. It's very easy to show that if the constraint set that constrains all the actions of everybody together is convex and compact, then this thing is guaranteed to exist. So at the very least, it is universal. And it is verifiable with the little info that agents have about their utilities. So what this point is trying to capture is agents finding themselves at the place where jiggling their actions locally doesn't give them utility. So they may say, okay, like at least as far as local perturbations are concerned, I'm happy with what I'm doing, given what the other agents are doing, okay? So this could be robots trying to control their joints, or agents in a gun or whatever. So, okay, so at least this thing is guaranteed to exist. It's a bare minimum, right? So if you don't like this notion, I'm not necessarily proposing as a notion, as the right notion, right? But I'm showing it as the natural generalization of what a local minimum is, or what a local maximum is. In the single agent case. And I'd claim that this is the bare minimum that a reasonable solution of these non-concave games should satisfy. It should at least satisfy that an agent cannot locally jiggle their actions to improve their utility, right? With information that they have about their utility. Question?
So you gave us examples. You gave us some examples before where the global Nash equilibrium wouldn't exist, but all those examples, if I understood them correctly, were non-compact. I'm wondering if there are examples that are convex and compact where a first order local Nash equilibrium exists, but a global one doesn't.
Yeah, so the example that I gave you earlier, this x minus x2 squared, also if the constraint is compact, like -1, 1, for all agents, it also doesn't have it. It's not a matter of.
But it will have a local Nash equilibrium.
It will have a local, yeah.
Okay, great.
And I think it's the 0, 0 point. Yeah. All right, so okay, so at least this is the bare bones of what the solution concept should satisfy. The question is it practically attainable? At least, so it looks like it isn't, right? I mean, the fixed points of gradient descent ascent, which is what people do in GANs, has this, as I was saying earlier, the fixed points of this procedure is tantamount to my solution concept. So I was saying earlier that people trying to do gradient ascent in these types of settings struggle with stabilizing the dynamics. So why do they struggle? Could it be that it's because of some underlying intractability? And one of the main results of this talk is that indeed this is the case, in a very strong sense. So even if you have two players and the interaction is zero sum, like in a GAN, but your utilities are non-concave, then any first order method, so any method that accesses utilities through first and second, so through zero and first order information, requires exponentially many queries in the dimension of the problem and the approximation to compute an approximate local Nash equilibrium. So this is a query complexity lower bound. It says that if any method that queries the utilities, making first order queries to them, will have to spend exponential time to give you even this very weak solution concept. Okay. So that's a query complexity lower bound. You may ask, okay, all right, how about second order or third order? Maybe I can spend some more time and get the Hessian and the third order derivative and so on and so forth. What happens then? So, not much is improved. I mean, so there's a computational lower bound that says that in the same class of two-player zero-sum games, any method, first order, second order, or whatever, needs super polynomial time in the dimension and or the approximation to find an approximate local Nash equilibrium, unless some complexity theoretic collapse takes place, which is that PPD collapses to P. So we have a query complex lower bound for first order methods, exponential queries, or a super polynomial lower bound for any method, first order, second order, or whatever. Now, I realize that PPAD is not a familiar class. It's not as famous as, the class that Karp was working on in the 70s. But it's in between P and NP. Okay, it lies somewhere in between. And it contains some difficult problems like finding approximate Brar fixed points of ellipsis functions, computing Nash equilibria, mixed Nash equilibria in normal form games. So games with a finite number of actions and players choosing distributions over those actions. And several other problems in combinatorics and topology. So our result, said differently, is that computing local Nash equilibria even in two-player zero-sum smooth non-concave games is exactly as hard as these two problems, and at least as hard as any other problem in this class. I'm not going to give a proof, but I want to give some intuition about why even two players are too many. All right, why is it that if you have a single agent trying to minimize a non-convex loss function, you can do that efficiently? While if you have even a two-player zero-sum interaction where people have non-concave utilities or equivalently non-convex losses in their own actions, that is a difficult problem. So to convey some intuition about the difference, the big difference between these two problems, I want to consider objective improving paths in this type of problems and also in this type of problem. So in a non-convex optimization problem, if you consider objective improving steps by the optimizing player, you ought to see the objective function decreasing. Okay, so here I'm showing how the objective values may look like in a non-convex minimization problem along an objective improving path that the optimizing agent may follow. Right. So what you see is that it's an objective improving path. So the function values have to go down. In particular, if the optimizing agent doesn't just make optimizing move, but moves that guarantee them at least some epsilon improvement. And if your objective function is lower bounded, then you're chipping away progress towards the absolute lower bound. So you are guaranteed to converge as you walk on such a path. And the number of steps is going to be polynomial in the 1 over epsilon, because you're chipping away epsilon. And there's if the function is bounded, there's an absolute floor, right? So that's what's happening, and this is roughly why gradient descent converges. This is essentially what it is. In a two-player zero-sum games, things are more funky. Okay, so here I'm showing you the objective value, how the objective value may look like in a two-player zero-sum game where horizontal moves are by a minimizing player. It's a zero-sum game. So one tries to minimize and one tries to maximize an objective function, the same objective function. Horizontal moves correspond to the minimizing player, vertical moves to the maximizing player. And I'm showing here possible values for the objective along a better response path by the players. So of course, horizontal moves have to decrease the objective, vertical moves have to increase the objective, because they correspond to these two players. And here are two interesting observations. So first of all, better response dynamics might be cyclic. This is a better response dynamic. So you cannot have a cyclic objective improvement paths over here. Over here, you could have cycles. The other thing I want to observe is that you could see repetition of values, even if it's not, even if a better response path is non-cyclic, you could see repetitions of values of the objective, like here, like 3, 2, 1, 1, 2, 3, 3, 2, 1, and so on and so forth. So in particular, querying the objective value somewhere along even a non-cyclic better response path doesn't offer much information about how far from the end of this path you are. So the end of the path would be a local Nash equilibrium, but the fact that these values can repeat themselves along this path is problematic. It doesn't give you much info about the location of these local Nashes. This is intuition. To turn this intuition into an actual query lower bound, what you'd like to do is to cook up an objective function such that a better response dynamics, you know, are a serpentine-like space-filling path in some ambient space, so with repetition of values, so that querying the objective anywhere on the path doesn't give you much info about the location of local Nashes. So we're not able to do this, to execute on this intuition. And instead, so rather than proving the query complexity lower bound first, we first establish the computational lower bound, the PPD completeness of against any algorithm. And the fact that our reduction was black box allowed us to inherit some query complexity lower bounds from the computation of Brouwer fixed points to this problem. So we first showed the computational result and then showed the query complexity lower bound. This is roughly why, though, 2 players are too many. I want to draw a philosophical corollary from this result, right? So again, I really tried to replicate the notion of the solution concept from minimization problems. So I really tried to replicate this notion of local minimum or local maximum, which has been driving progress in single agent deep learning, right? Where you know, what you do, like the paradigm there is you pick a model that is maybe very complex. You collect a lot of data and get access to a supercomputer, and then you train the heck out of your loss function using gradient descent or some variant of that method. So here I tried to replicate this in the multi-agent setting, and I failed very badly, right? So I extended this notion of local minimum to the multi-agent world, so giving rise to these local Nashes. Which is, again, a very weak solution concept, not necessarily what you would like from your GAN or what you would like from your robots interacting with each other. And nevertheless, I already hit lower bounds. So my corollary from this is that in the multi-agent world, and this is a call to arms, really, in the multi-agent world, you need to do a lot more work in understanding your underlying application with domain experts in order to model it appropriately, understand how your learning model should look like, not just any arbitrary neural net, understanding what are meaningful solution concepts that maybe bypass these lower bounds, intractability results, and coming up with an algorithm that attains these solution concepts. And I think only then we might get more successes like AlphaGo and Libratus, which are not just neural nets playing games, but they actually, in how these are trained. In fact, Libratus has no neural nets in it. But the way these algorithms are trained is actually using the structure, the game theoretic structure of the corresponding games. All right, so that's my little philosophical corollary. And before I conclude, let me spend a little time, a few slides on some progress towards realizing this, okay? And that progress pertains to the problem of multi-agent reinforcement learning, which is the multi-agent generalization of reinforcement learning. So, right, so what, okay, so, and in particular, just in case you are not familiar with the background, let me tell you a little bit the mathematical foundation of reinforcement learning and multi-agent reinforcement learning, which are correspondingly Markov decision processes and stochastic games. So in a Markov decision process, you have an agent and a system. The system has state. The agent submit actions to the system and get back a reward that depends on the current state and the action that they chose, and a state transition that follows the dynamics of the system. Commonly in Markov decision processes, you care about stationary Markov policies, which specify, which recommend an action, a distribution of actions for every state. These are called Markov and stationary because they don't depend on the time of the interaction, what little t is, they're just stationary. And they're Markov because they don't depend on the history, they just depend on the current state. These types of recommendations are called stationary Markov policies. And what agents typically try to do in these kinds of settings is to maximize their long-term discounted reward. So an agent wants to find a policy such that over an infinitely long path that starts at some state as not, and at every step has the agent choose an action from their policy and gets a state transition from the system dynamics. So you sample an infinite path like that, and you accumulate the rewards that the agent gets along this path, discounted by some gamma at every step. So this is what we do in MDPs. Stochastic games are the n-dimensional n-agent analog of that. So you have many agents submitting actions to the system. The state transition depends on the current state and the actions chosen by everybody. And the rewards to an agent depend on the state and the actions chosen by everybody. The analog of a stationary Markov policy here specifies a recommendation of actions for everybody at every state. And again, the agent's objective is for an infinitely long path sampled following the recommendations of the policy and the state dynamics, the reward that an agent accumulates. So it's the exact generalization of the single agent setting to the multi-agent world. Now, what is a good solution for this? So over here, the good solution is find a policy pi that maximizes this value for the agent. What is a good solution over here? Well, this is a game, so there are many kinds of solutions. Here's one proposed by Shapley and studied a lot in game theory. It's stationary Markov-Nash equilibrium. A stationary Markov-Nash equilibrium is a policy pi with the extra property that it's a product measure. So every agent at every state independently samples their action. Okay, so this is the product measure here. So you want to find a policy pi that's a product measure so that every player I, for every player I, and for every alternative policy that they may want to use rather than their policy in this product measure, their value would decrease or would not increase if they were to switch to that policy pi tilde. Now, interestingly enough, these things exist as long as you have non-trivial discount factor. And this is quite surprising. And this is kind of like motivates this part of the talk. This is quite surprising because the values are non-concave in the policy pi. Policy pi, affects the trajectory that you follow, and because you may come back to states, your utility is not concave in the policy pi, or your own policy in this measure. So in this product policy, so it is surprising that these things exist, but they do exist. And what I want to figure out is, can they be computed, right? But here's a weaker notion of equilibrium called stationary Markov coarse correlated equilibrium. This is the same thing, except you don't restrict the policy to be a product measure. You allow, you want to find a policy that might correlate the action chosen by people at every step. That's a stationary Markov coarse correlated equilibrium. So what do we know about computing optimal policies here and optimal and equilibria over here? Where on the single agent case, we know a lot. There is a lot of methods. There are a lot of methods for finding optimal policies, and a lot of recent work also that think about the problem of learning policies in settings where you don't know the environment, but you have to learn a policy, learn as much about the environment as you need to learn a good policy. On that side, though, two things. One, stationary Markov-Nash equilibria are definitely hard, right? Because stochastic games are more general than single round, like normal form games where there's a single state. And over there, finding Nash equilibria is pretty hard from my work and other people's work. So definitely you can't hope to compute stationary Nash equilibria in this case, all right? So work has studied two settings instead. One is the two-player zero-sum case of Markov of stochastic games, where the problem is tractable, and at least as far as computing approximate Nash equilibria is concerned, or correlated equilibria, like this coarse correlated equilibria I was talking about before. However, in contrast to normal form games, so games with a single state, where coarse correlated equilibria are a very nice thing, they're computable by linear programs, and you can arrive at these types of equilibria by running no-regret learning. So coarse correlated equilibria in single state stochastic games are very, very tractable. Experience with stochastic games shows that they're not as tractable in this case. At least existing algorithms, there are no known algorithms that are polytime, and if you are also learning polysample complexity, except algorithms that violate one of these properties, like either outputting non-Markovian or non-stationary policies. So what I want to ask here is why? What is it that single state games are tractable? And the moment you have a multi-state interaction, the problem appears to be challenging. So the main contribution of this segment of the talk is that there is a reason why that happens, and it's pretty surprising. We show that even when you have a two-player stochastic game, even when the discount factor is a half, which basically means that the expected interaction is 2 steps. Okay, so the discount factor is huge. You expect to interact with the other agent for 2 steps. Okay, the problem of computing coarse correlated equilibria becomes pretty hard. All right, so like one state, very tractable. If you expect to interact with the other agent 2 steps, it becomes intractable. This is very, very, very surprising. And of course, if you have longer interactions, the problem is even harder. So it's even more intractable. This is quite surprising. In the interest of time, I'm not gonna give you the sketch of the proof, which was only gonna be this one, and just conclude with some thoughts of what might be computable, or actually, let me skip that in the interest of time. So we have some positive results in the paper where we show how to learn non-stationary Markov CCEs in this case. Non-stationary Markov CCEs are policies that are Markov, but they are time dependent, that change with time. So in that case, we provide efficient algorithms for learning such policies. And that I think is an interesting thing to do in this case, because multi-agent reinforcement learning settings are very important, and the fact that stationary Markov CCs are not even tractable, not even these are tractable, would require you to compromise to something like non-stationary Markov policies. That's all I had to say. I think that the broader topic discussed in this talk is very unexplored. As I was saying earlier, game theory has broadly focused on cases where utilities are concave. in one's own actions. And there are many directions to be explored here, a very fertile ground and with important practical implications. So I encourage everybody to try to think about it and work on it. So thank you very much.
Thank you, Kostas, for the great talk. And I'm monitoring the chat. If anyone watching online has any questions, please type it in the chat. Otherwise, I'll take questions from the room first.
So what about just the last thing you were telling us about? Either I misunderstand it, or it seems to me you're overstating the result, because you're making this distinction between a game that's unrepeated and a game where you expect two interactions. But it seems like expect is doing a lot of work there, because if I know that there are two interactions, it collapses back to a normal form game, right? So, I mean, then it would really just be an extensive form, an imperfect information extensive form game with two interactions, and that would have an induced normal form that was finite, and then you'd be back in the single interaction.
Correct.
So it seems like really what's going on here is that the expectation isn't very important, and it's the fact that the game can go on infinitely, regardless of the discount factor, that must be driving the result.
That's not the important distinction. If you try to write it as a normal form game, the equilibria that we'll get are non-stationary. So there will be like the ones discussed over here. So like if you try to, I mean, it's not the expectation of two interactions that is really doing the work. The intuition is that the fact that you're shooting for this Markov stationary equilibria is the problem. The moment you relax your notion to non-stationary, so like if you were to write a normal form description of this two-stage or multi-stage game, the types of equilibria you would see, would not necessarily be Markov stationary. And, that problem is tractable. And the challenge here is to, can you, if the game is unknown, can you learn it? And this is the contribution of this slide I didn't talk about. But you're correct to say, if I can write the normal form, I could solve that, but it's not going to be a stationary Markov nash, a Markov correlated equilibrium.
So even if you knew the game stopped after two interactions, but you wanted to do this stationary Markov concept, you'd still be in trouble?
I think you would be. I mean, I haven't. You would definitely if you write an LP, you'll definitely get a non-stationary nash, a non-stationary CC. I haven't looked at specifically to rounds. Okay, so that's interesting. But again, this normal form description misses the stationarity. Yeah.
Also related to that, but you also want the reduction. Maybe I misunderstood the question, but you want the reduction in the other direction, right? You want to take an arbitrary game and reduce it to this two-stage game or something. And
for the hardness result, so he's talking about upper bounds. That's why he's complaining about why did this complexity arise? And indeed, the complexity arises because of the stationarity of the policies that we're requesting. For the lower, if you want to prove a lower bound, you have to start with an arbitrary PPAD complete problem and reduce it to a multi-stage interaction like the ones.
And that's what you do in this.
That's what we do there. Yeah.
Any other questions? I had one other curiosity question. So in this game between GAN and discriminator, current state of the art with neural networks, who's winning?
So there are very good GANs out there, but maybe motivated by this challenge that I'm talking about, there is a lot of work in providing frameworks for training deep generative models that are not based on a gain, but purely minimization problems. So there are several recent frameworks that train deep generative models, writing down a minimization problem, these are called score-based models or flow models, and they are competitive to the practical behavior of GANs. Is that a question?
Yeah. I want to continue on a previous discussion on this non-concave min-max optimization problem. So you mentioned there may not be equilibrium, right? But also some audience mentioned if we just discretize the entire space, then there could be equilibrium. So essentially it corresponds to you use some mixed strategy. Right?
Correct.
And
yes.
Yeah, I mean, I think it. So for my first question is if you min-max optimization, min-max optimization is on a constraint set, then there should be a mix.
Right. So that's a great question. So first of all, like this is a bit beside my specific talk because I'm not talking about GANs specifically, but indeed, like if you discretize the space to a finite number of possible parameterizations of the GAN and consider distributions over them, if your set is finite, definitely there exist distributions over these finite spaces where that are equilibria. Now, another thing you may do, which is a little bit more sophisticated, is to not discretize, but still ask questions about whether mixed Nash exists. Now that goes up against the lower bound of guess the larger number game that I mentioned earlier. But like recent work that I have with Noah, I think it's so in stock this year, gives conditions under which equilibria exist in this infinite games, mixed Nash or mixed correlated, or correlated equilibria in these games. And the answer relates a little bit to the online to Littleson dimension and sequential or Demark complexity of some function classes that relate to the underlying game. So that is definitely something to try. My perspective is for GANs that wouldn't make sense, but theoretically thinking about this question is very interesting, and there are many interesting things to consider there.
Yeah, and maybe just a second question. So, so is it possible to like circumvent this difficulty by doing some like improper learning? So do you really maintain some mixed model?
You're not talking about games, right? They're not concave. You're talking about excuse me.
Maybe just consider like min-max optimization, but instead of just optimizing the model, I'm maintaining like a mixture of model. It's kind of like some mixed strategy.
Still mixed strategy, though.
Yeah,
not pure strategy.
But so I think it's naturally like maintain some mixed model.
Yes, I mean, if you're going to consider mixed strategies, there's a lot of things you can do proper and non-proper. I mean, as I was saying earlier, this relates to unlearnability, and in unlearnability, proper and non-proper makes a difference. So there are things you can do in that space.
I know that both of the papers have been published very, very recently, but in the case that you have a comment, I would like to learn about it. There is a very concurrent work of Aaron, Vidya, and Yuja that speak about the term-based games.
Right. And
where there is the issue that actually because the term-based MDP, in each state you play exactly one player. Actually, CC is I would like a comment to understand what are the differences.
What are the difference between the two papers?
Between those two models.
Right. So this is in the part that I didn't get to. So there's simultaneous work by Jean Kumar and Sidford. They show the same result, except these two becomes n. So it's and basically, okay. So like roughly speaking, the difficulty is that in the complexity proof, one thing you can do is you can start with like a n-player game and to reduce to this stochastic game. And the easiest thing to do is to replicate every agent in the game you start with a state in your stochastic game and assign that state to a single player moving there. Okay, this is where round based. So so if you want to prove a hardness result for n-player stochastic game, so if there's a number of there is a single agent playing at every stage every state of that stochastic game. You can get that more easily, and a lot of the hard work we need to do to prove the two-player game is to actually argue that you don't need to assign a different player playing in every state, but like you can have players playing in multiple states where they have to take into account like my actions here in the state, what impact would how would they influence the probability that I reach other states where I also am playing, and so on and so forth. So, the two results are similar. The difference is that here you have two agents, so it's an easier problem that you show is hard. Here you have equal number of agents and states.
I see. Thank you. Thank you very much.
Thank you for the great talk. So in the last couple of last decades, I think like deep learning has been pretty disrespectful
Okay.
with like lower bounds.
Oh, okay.
You know, we had, it was supposed to be hard to find global minima.
Yeah.
It's supposed to be hard to distinguish local minima with saddle points. So what about yours? Do you think deep learning is actually hitting your lower bound, or because in practice, for instance, in the result you showed, we are reaching something bad for the generation, but it's sort of a fixed point, no?
Okay, I guess okay. So you're talking about two different things. Like, are we talking about GANs? Or are we talking about general non-concave games?
Yeah, I would say like anything where there is a deep learning application. Yeah.
I mean, anything.
So GANs, let's say GANs.
There exists a deep learning setting that's multi-agent where there's no problem, right? So there exists, right? So like the question is, I guess the point of this talk is like in non-convex minimization problems, you are guaranteed to converge to local mean in poly 1/epsilon steps, right? So you have like whatever model you write, you are guaranteed like the single method of gradient descent will give you an epsilon min, local mean in poly 1/epsilon steps. In the result, not this specific result, because this is a PPD hardness result, but my query complexity lower bound I was talking about earlier, you cannot have such a guarantee. Like there's no, and that is problematic from the perspective of having a framework for multi-agent learning, right? So like in single agent learning, write any model you want, put it on TensorFlow, gradient descent, you will get an epsilon local minimum. Over here, you don't have, you lose this guarantee. That's has nothing to do with complexity. It's just a query complexity lower bound. You don't have such query complexity lower bounds for minimization problems. For minimization problems, poly 1/epsilon suffices. Over here, you need exp 1/epsilon. That's a query complexity lower bound. That's not a hardness result. Now, if you also believe, the hardness of p-pad and that, like that, now you start talking about average case and so on and so forth, then, maybe there are some if then else's, but I think this query complexity lower bound is very stark, very problematic. I mean, it just removes the guarantee you have from gradient descent in minimization problems.
Let's take one question. There's a couple of questions in the chat from the same person, so I'll read this. Is there a way to have zero-sum game in the learning environment? And what are the causal effects of an agent's actions in RL environments? Can our measurements of an agent's actions affect its learning environment?
What was the question?
Okay, let's do it. Is there a way to have a zero-sum game in the learning environment?
In the reinforcement learning one? Yeah, definitely there is. I mean, like two players playing basketball against each other is a two-player zero-sum reinforcement learning problem. And what was the
second question is, what are the causal effects of an agent's actions in RL environments? And can our measurement of an agent's actions affect its learning environment?
Oh, yeah. So the causal, I mean, I guess, the causal effects is like what you anticipate that your actions will incentivize the other agent to do. And they're thinking about the same thing. So you have this fixed point interaction. And this anticipatory planning is what introduced a lot of the complexity of this problem.
Yeah. Okay.
One thing I should mention though is that, which also is pretty surprising, if the game is like in the classical setting studied by Shapley, there is a min-max theorem for stationary Markov Nash equilibria, which is also another pretty cool thing that these stochastic games have. Like zero-sum stochastic games have a min-max theorem for stationary Markov Nash equilibria, right? So min and max can be swapped, which is cool.
And for your lower bound, is there an approximate notion of stationarity that will bypass it?
Which lower bound? For the general?
The p-pad for two players, if you only require some sort of like epsilon approximate stationarity.
Stationary, I see. Local station. I mean, so this is for approximate. Like we say that even for constant approximation, this is hard.
Where the epsilon goes to your best response or to the stationarity?
The value. So like you want a value. You want that no switching your policy can give you better value.
If you allow for time sensitive, but you have like approximate stationarity, you cannot.
Oh, approximate stationarity. I see. I see. Sorry. Yeah.
Yeah.
So this epsilon is not on stationarity, it's on the value. So that's a good question. Approximate stationarity. I think there are stuff you can do if you violate the station. I mean, like there's this result, right? That any game, you can truncate the horizon at, you can pretend that there's no future beyond 1/1 over gamma steps. And your stationarity can be at most, needs to only be at most this much. Like you only need to remember this many things in the past. Now you're asking about like what, like memory 2 or 3 or something small.
Maybe the distribution of actions could change at most by at most something in between.
Or like some measure of stability. My guess is that this wouldn't cut it, because I'm pretty sure the proof can be robustified to not care so much about the most recent history. But I have to think about that. That's a great question. But a general comment though is this, that you only need to remember this many steps because of the like if you were to allow more memory. Yeah.
And also if you have some form of like fast mixingness for any action, then would that be enough?
Fast mixingness meaning
some strong fact, like no matter what action you take, there's like, from every state I go to every other state with some probability.
I don't think that would cut it, probably, because I'm pretty sure we can hook up everything and still have the hard distance hidden there with a lot of hooking up, and I don't think that would fix it either. But okay, great questions. Yeah, these are speculative answers.
Yeah, thanks everyone for the great questions and discussions. Maybe we'll, if there are further questions, probably take it offline. And thanks again to Kostas for the great talk and discussion.
Thanks.